All right. We are going to get started with the final panel of the day. At one point this morning, it was a completely intact panel. We had absolutely everyone. Then John Quigley, who was trying to escape the snow of Philadelphia, his car broke down. I think that's right, John. You can defend yourself when you're on in a few minutes. Make sure this doesn't fall off. This wants to go back full screen up here, I think. Lizzie, what do you want? I'm not touching this to get it to full screen because I'll mess something up. But oh, that's so easy. That's why you need a lawyer. All right. For the final session on carbon capture and storage for natural gas and coal, the fourth of the four technologies really that we're looking at. Very happy to introduce yet another member of the advisory board for the conference, Aimee Curtright from RAND here in Pittsburgh, who has been a great help on this. And as a side with PEC, we've also been talking about about legacy issues from coal, natural gas, oil, as economies change and times go forward in an extractive state like this. So, Aimee.
All right, well, this is probably more daunting than being the panel that stands between you and lunch. We're the panel that stands between you and a beer. So we will endeavor to move through this quickly. I'm going to skip the bios. All the panelists have the bios on the same page, so please read those. And I'm just going to make two comments that apply to this panel as well as all the panels throughout the day. And one is, to state the obvious, it's pretty clear we have our work cut out for us in deep decarbonization for electricity. It's also pretty clear we have a lot of technologies to choose from. None of them are perfect. Some of them are less perfect than others. They all have drawbacks and limitations. And carbon capture and storage is certainly no exception to that rule. I think unlike energy efficiency and renewables, which give everybody warm, fuzzy feelings, CCS kind of falls in that visceral response camp. I don't know how nuclear versus CCS rank in terms of giving people the heebie-jeebies, but it's just something that people don't like to think about doing large-scale geology experiments on the planet. I'm one of those folks. But as you'll hear in this panel, this is a really promising technology. It is something that can potentially be deployed globally at large scales, provide firm power at large scales. And increasingly, it's looking like we can't get there without it, especially if we start to think internationally. So with that, I will turn the mic over to John Quigley to give the introductory remarks.
Hope I'm coming through. Let me just plow through. First of all, I want to thank PEC for this visionary conference. This is an important conversation, and I really appreciate PEC's willingness to convene all of you for attending. Sorry I couldn't be there. I was actually on my way this morning, and I was about to turn onto the turnpike, and my car decided not to cooperate. So after getting towed home, here I am, so I will try to make the best of it. Next slide, please. What I'm not going to talk about this afternoon are a couple of important pathways to carbon capture and storage, and that is afforestation, that is planting trees, which is probably one of the best things we can do to take carbon out of the atmosphere, and also things like storing carbon in soils. In Pennsylvania, the Rodale Institute has done some incredibly important work on what they call regenerative organic agriculture and its ability to sequester carbon. I'm not going to talk about those, but I really encourage folks to take a strong look at those topics as well. Next slide. Want to define terms? Carbon capture is the process of capturing CO2 emissions from large stationary sources. Next slide. And that typically assumes coal-fired power plants, but next slide, it has expanded to embrace other industrial facilities from refineries, steel, cement plants, other industrial sources. And next slide, what I think is most important, capturing CO2 emissions from natural gas-fired power plants. That's where Pennsylvania needs to go. There are enough natural gas-fired power plants in the permit queue at DEP to supplant all of the remaining capacity of coal-fired power plants in Pennsylvania. So in our state, and I think nationally, if we're going to meaningfully reduce carbon emissions, we have got to look at CCS for natural gas-fired power plants. Next slide. The other thing that I will talk about in a little bit of detail is the idea of bioenergy and carbon capture and storage, and that is combining bioenergy combustion for electricity generation to carbon capture and storage. Next slide. So after we capture the carbon, then we compress it, and compress the captured CO2 into supercritical or liquid form. And that involves low temperatures and high pressures and some big energy penalties, which I'll talk about. And then either injecting that captured CO2 on site, using it on site for storage or for utilization for other industrial processes, or transporting it elsewhere for storage or utilization. Next slide. I'm going to take a look at the storage part of the equation. Storing CO2 geologically involves injecting this supercritical CO2 into a number of geologic formations, saline aquifers, shales, very important for Pennsylvania, oil and gas reservoirs, and unminable coal seams. The U.S. Geological Survey has estimated that the United States and Canada alone has thousands of years of storage capacity. As I'll talk in a couple of minutes, Pennsylvania has at least 500 years worth of storage capacity geologically. Next slide. The utilization component. There are a number of industries that are essentially aborning in this country and around the world that would utilize captured CO2 as a feedstock for other industrial processes. The one that is used most prominently right now in this country is enhanced oil recovery, EOR, where this CO2 is injected into formations to force out oil that resides in pore space. And that's the way that CO2 is being driven economically at this point. Next slide. There are, however, a number of other utilization pathways that need to be explored, that need to come to industrial and commercial scale, from beverage carbonization, using CO2 for greenhouses. Big deal in Pennsylvania, coming attractions is marijuana growing. And there is some data actually that suggests that using captured CO2 to enhance the atmosphere in greenhouses for marijuana makes actually the marijuana more potent. So something to look forward to for some. But captured CO2 can also be used in plastics, for cement manufacturing and concrete, for low carbon transportation fuels, other chemicals. Next slide. And the thing that I think is most important for Pennsylvania is to consider the use of captured CO2 for fracking. Right now, we're using an enormous amount of water. That amount is growing per well and in terms of gross numbers. And the idea to get to waterless fracking using, for example, CO2 is something that I think needs a lot of research and some real policy impetus. Next slide. There's actually an X Prize that is being funded right now. X Prize, as many of you know probably, is an effort that involves a number of huge investors that are trying to do globally important work. And there's a $20 million X Prize that is put out for award in 2020 to identify technologies and utilization pathways for captured CO2 in a couple of different tracks, capturing CO2 from coal plants as well as natural gas-fired power plants. There have been 47 entries in the X Prize competition. That was narrowed down to 27 in round two, and presented on this slide is the pathway for the X Prize. Next slide. In terms of potential and need, the technology exists currently that we can capture upwards of 90% of CO2 emissions from both power plants and industrial sources. And according to the International Energy Administration 5 years ago, CCS comprises about 1/6 of the CO2 reduction that's required by 2050 to meet what was then the global CO2 emission targets. So it's a big portion of the world's planning in order to achieve, at least potentially, a 2 degrees centigrade future. Next slide. There are, however, some limitations. The capture technology is costly. To run the technology, compress the CO2 into supercritical form, and then inject it requires energy. And there's what's called an energy penalty of upwards of 30%. In a typical coal-fired power plant, that translates into very challenging economics for plants that intend to capture their CO2 emissions. There are other issues like storage liability long-term. The CO2 that is injected has to essentially reside downhole forever in these formations. And the long-term storage liability, as well as the measurement, the monitoring, the verification of operations of these facilities, as well as post-closure, essentially forever, has been challenging. And then there are some logistics that are involved that I'll talk about relative to Pennsylvania's experience in particular. Next slide. The important point to emphasize when you talk about CCS and CCUS is that technologies really aren't new. The technologies across the value chain are well known. They've been operated at various scales for as long as decades. The first big industrial scale carbon capture and storage facility was in Sleipner in Norway. That's been operating for 20 years and has sequestered successfully more than 17 million tons of CO2. And the individual applications have been used in industrial processes for decades. There are essentially projects in the U.S. Operating since the 1970s. Unfortunately, most of them, for example, the enhanced oil recovery operations, have used, ironically, naturally occurring deposits of CO2 rather than industrial sourced sources of CO2. And the technologies have only been put together at an industrial scale, that is 1 million tons or more a year, in only a small number of applications. And even at 1 million tons, when you look at the output of a typical coal-fired power plant, that's not the scale that is needed to get to real 90% capture. Next slide. There are about 38 large-scale CCS projects in the world in some stage of planning, and about 16 of them are actually operating. Next slide. 12 of them are in the United States. 3 of them happen to do with energy generation. The source of these next couple of tables comes from the Global CCS Institute, which actually has a kind of a running tabulation of all of the CCS projects and CCUS projects in the world. Really great source if you're interested in this subject. Next slide. You will notice that of all of the projects that are planned in the United States, they all have to do with enhanced oil recovery. The economics and the challenging economics of these projects are such that you have to have a back-end revenue source to make these projects viable. And in every case in the United States so far, that has been enhanced oil recovery. Again, enabling additional recovery of oil reserves as a result of the carbon capture has been the only way that this technology has been viable so far economically in the United States. Next slide. You will notice that one of the projects that I highlighted, the Petronova carbon capture project, is actually the world's largest. It was brought online in late last year, and hopefully it was brought online on time and, critically speaking, on budget. So there is at least one project in the United States that offers some hope in terms of the future of carbon capture and utilization. Next slide. A couple of other projects, and we'll go quickly to the next slide. You'll notice that, go ahead, advance one more, please. One of the last projects that I mentioned in the U.S. happens to be the Kemper County project that essentially is a fail, if not an epic fail. It's about $4 billion over its budget, almost more than double its original budget. And they announced that was what was originally a plant that was based on coal-fired power and now is not economically viable unless it runs on natural gas. So we have some mixed success. We have the Petronova facility, which is on time and on budget, and in this country as well, the Kemper facility, which is essentially an epic fail. Next slide. In the United States, there's a couple of other projects as well that are in the planning stages in Texas, and as well. Next slide, please. That Net Power facility in Texas is one that is particularly hopeful. It's intended to burn natural gas to generate electricity, capture all of the produced CO2, and the proponents are claiming that the project will come in for the same cost as modern gas-fired natural gas turbines. If they can prove that, that is potentially a game changer for CCS in the United States, and it's certainly a project that bears watching. Next slide. In terms of utilization, there are 17 utilization projects around the world, 2 of them in the United States, one in the food and beverage industry, and the second in mineral carbonization. I won't get into the details of any of those projects. If you want to drill down on any of these, again, the Global CCS Institute is a great source for information. Next slide. So how do we get to a 2 degrees centigrade future? And what is the role of carbon capture and storage? Next slide. Well, as I said, there are about 16 projects that are currently operating and another 22 that are planned around the world. But according to international sources, to even have a prayer at a 2 degrees centigrade future, to keep warming below 2 degrees centigrade, you need 4,000 of these facilities in the next essentially 20 years or so. So we are a long way from where we need to be in terms of CCS. Next slide. Again, we are really not close. And in fact, just last year, there was a report that was put out that compares the goal of the Paris Agreement to pledges of its signatories and where do we stand. And this report, the Emissions Gap Report of 2016, said that we are likely facing the last chance we have to limit global warming to 1.5 degrees centigrade. We're pretty much at the end of our rope in terms of technological solutions and international efforts to limit warming to preferably 1.5, if not 2 degrees centigrade. Next slide. The International Energy Agency last year put out a report that summarizes the international experience on carbon capture and storage. Next slide. And what they concluded last year was that deployment of CCS will not be optional if we are to successfully implement the Paris Agreement. So the international consensus is basically that without CCS, we're cooked. I think one of the previous speakers says we're burnt toast, and that's probably not a bad analogy at all. Next slide. So again, we're not moving on CCS and CCUS nearly fast enough. The pace has to accelerate. We're certainly way off target at this point. The technologies are proven, the technologies are well understood, and they are essentially cost effective, and I'll talk a little bit more about that in a second. But according to the Global CCS Institute, in a report they issued last year, what is needed is policy parity. That CCS and CCUS deserve the same kind of recognition and incentives as clean energy, especially renewable energy. And clearly, we are not at that point at all right now. Next slide. Because of our lack of progress on CCS and CCUS, and because of its essential role in limiting warming in either a 1.5 or 2 degrees centigrade world, there's growing conversation about carbon removal. The necessity to keep emissions below a 2 degree centigrade pathway to start taking carbon out of the atmosphere. Next slide. And that brings us to the subject of bioenergy with carbon capture and storage, so-called negative emissions. And the idea is you burn biomass as fuel while capturing the CO2, storing it underground. And the idea is because you're using biomass, you're actually, essentially, you start with a net negative or neutral energy source. And then when you couple it with carbon capture and storage, you're actually essentially removing emissions from the atmosphere. Next slide. My assessment of that is not so fast. There are vast requirements for land. When you look at bioenergy, we actually did some work when I was at DCNR in the Rendell administration on sustainable biomass harvest. in the idea of using biomass as an energy resource. And there are certainly, from a conservation standpoint, some real hard limits on the potential for BECCS, bioenergy with carbon capture and storage. Primarily, forests are not fuel. We can't mow forests and use them as fuel and realistically expect to have a meaningful impact on reducing atmospheric carbon. The land area requirements of biomass energy are extremely significant and imply at least competition for not only conservation but food and crop areas. There are other issues with bioenergy, the pollution emissions from bioenergy, combustion, the particulate matter that comes out of bioenergy combustion is a big deal and frankly has been somewhat understated and understudied and undervalued. But the long and the short of it is that if BECCS is to be deployed at a scale sufficient to be a significant global player, it's going to imply intense competition for food and habitat and conservation needs. And the result of that is that other technologies like direct air capture are being increasingly looked at as solutions to this negative emissions scenario. Next slide. Now, when you talk about the policy supports for CCS, I'm going to invoke Julio Friedman, who was the CCS expert in the Obama administration. He's now at the Lawrence Livermore Lab. I've clipped some Twitter posts, and that seems to be the big deal today, although I won't use the word sad, but a lot of folks like to go on Twitter and clip posts and make comments. Well, Julio, I think, has made some very provocative comments here that in terms of the economics, there are technologies right now, natural gas, combined cycle technology, and CCS that are cost competitive with renewables, or at least potentially. They're pretty provocative statements that frankly need to be ground truthed, that need to be researched, that need some policy impetus. Next slide. Julio goes on to say that there's really no mechanism around the world today to recoup the costs that are involved in a CCS plant. For example, in 2014, the U.S. spent $44 billion on production tax credits for wind power, nothing on CCS. And over the past decade, the world has spent over $2 trillion backing renewable energy and $20 billion on CCS. So there is a tremendous policy disparity in terms of these alternative solutions. Next slide. So in sum, the challenges basically are commercial, not technical. Again, the technology is well known. We need technological advance, to be sure, but we also need government support in terms of resource and demonstration and deployment, in terms of government support, outright subsidies, and in terms of policy development. Next slide. Now, ironically, Pennsylvania used to be a leader in CCUS, and this goes back a decade to my work in the Rendell administration under Secretary Michael DeBurr-Redinas at DCNR, and then I was fortunate enough to succeed him as secretary for the last couple of years of Ed Rendell's term. Next slide. With the help of PEC, PEC was a huge and important partner in this work with DCNR. A decade ago, Secretary DeBurr-Redinas convened the Carbon Management Advisory Group to try to understand what the role of the Commonwealth's Natural Resource Agency might be in a carbon-constrained future. And it put out this report in May of 2008. Next slide. And that report made recommendations in 4 categories. How do we manage our forests, both public and private, to sequester more carbon? What is the role of landscape conservation in a carbon-constrained future? What are the role of registries? We took a real strong look at, for example, RGGI. We looked at what the work that was being done in California to incentivize carbon in all of its forms. And we looked prominently at the role of geologic sequestration in Pennsylvania in a whole series of studies that was a kind of a follow-on to what we called the CMAG report. Next slide. You got to remember the context then 10 years ago, CCS was constrained to pilot projects, demonstration scale projects that were very expensive, that were certainly not at commercial scale. There were questions about how much storage capacity do we really have? The science was not as well developed as it is today. There were big questions about the safety long-term of storing CO2, and there was huge unanswered questions about long-term liability for that storage. Next slide. So we put together some, I think, some of the most seminal work on CCS in the country. Certainly it was among the most advanced in the nation at the time. The first was we looked at, from a geologic standpoint, what are the opportunities to sequester carbon in Pennsylvania from a geologic standpoint. We did a deep dive on Pennsylvania's storage capacity. Next slide. We also took a look at the risks of that storage, trying to address what at the time were some only beginning to be articulated questions about long-term liability and public risks of releases and so on of stored carbon. I know Bobby McKinstry is in the room out there in Pittsburgh today. Bobby was very prominently involved in the assessment of this risk assessment that we compiled to look at what are the issues around geologic sequestration in Pennsylvania. Next slide. And you also have to remember that the big issue 10 years ago was scale. There were very few projects that are operating at 1 million tons or more annually of stored carbon. So we tried to kind of break that logjam at DCNR, and we partnered with the Clinton Climate Initiative to assess the idea of a carbon network, a first mover carbon sequestration network that would hopefully take advantage of economies of scale, of shared infrastructure. And we assessed the technical and economic viability of this idea of a CCS network. And so we partnered with the private sector, with 5 coal-fired power plants that shared under a non-disclosure agreement real engineering data. There were a number of other partners involved that are all depicted in the Clinton Climate Initiative report. It was all done pro bono, but a tremendous amount of pre-feed level engineering analysis of this idea of a network. And the goal of it was to get to large-scale carbon capture and storage faster by capturing economies of scale, by capturing the benefits of shared infrastructure, and very critically for Pennsylvania, winning the early mover benefits of being a CCS leader. Basically, we thought that with the engineering and intellectual capital that we are blessed with in Pennsylvania, schools like Carnegie Mellon, for example, there was a tremendous opportunity for Pennsylvania to be the home for carbon capture and storage technology and for the manufacturing jobs that would tend to leadership in CCS development. Next slide. So the Clinton Climate Initiative put out this report in November 2009, assessing the viability of a large-scale CCS network in Pennsylvania. Again, it was at 5 coal-fired power plants retrofitted with carbon capture technology, transmitting the captured CO2 to a centralized geologic storage facility. Next slide. And the conclusions were these, that Pennsylvania had, we calculated, at least 500 years worth of storage. And that was at then current emission rates with the advent of natural gas-fired power and the supplanting of coal. We have more than 500 years worth of geologic storage capacity in Pennsylvania alone. The conclusion from the risk assessment was that the network could be developed safely. And the Clintons and all of the partners that were involved in that study concluded that this integrated network, the CCS network, could be very cost competitive compared to what was then proposed or existing CCS projects. There was a very significant delta of around 30%. We are coming in 30% cheaper, at least at a pre-feed level of analysis, than any other global carbon capture and storage project. So there was tremendous potential, tremendous economic potential in this idea of CCS networks. And our studies at DCNR also identified some challenges. Assembly of pore space. the rule of thumb operating then about 10 years ago was that one 500 megawatt coal-fired power plant capturing 90% of its emissions for a completely 40-year operational life needed one 300-foot thick geologic formation, 100 square miles in area. So the logistical challenge of assembling the necessary pore space by any operator or a network was daunting. Now there happens to be an industry that is assembling and has assembled large-scale pore space in Pennsylvania, and it happens to be the shale gas industry that has leased about 2/3 of the land area of Pennsylvania in general terms. So that there is an opportunity in the shale gas revolution, and it's what it has done in assembling pore space to actually advance this idea of a CCS network in Pennsylvania. That concept needs to be explored. In our work in 2010, at DCNR, we also identified opportunities in Pennsylvania, particularly in Greene County, to do enhanced oil recovery. We talked about carbon capture and utilization, and frankly, I think we were one of the first folks to identify the potential for CCUS anywhere in the country, and I continue to be very proud of that work. Next slide. Another piece of work that followed on from that, we were invited, DCNR was invited, and I participated along with fellow staffer at DCNR, Gretchen Leslie, with the World Resources Institute that put out a report about community engagement, how to cite CCS projects. And obviously, given the challenges that we're seeing in Pennsylvania with things like pipelines, the idea of a CCS network was daunting at the time and calls into question the ability of project sponsors and governmental entities to achieve some level of public understanding and support. So the idea of public engagement around how to do these projects was incredibly important. And WRI in November 2010 put out this report, which I think holds up very well and has not aged at all. It's a very important piece of work, and I was proud to be a part of that work as well. Next slide. That's essentially it. Here's my contact information at the Kleinman Center. I think to wrap up, there is tremendous potential to dust off the work that Pennsylvania has done on CCS and CCUS and public engagement and advance it as part of a portfolio of strategies to get us to a decarbonized future. We certainly have assets in Pennsylvania that lend itself to more exploration of this topic. Thank you very much. And again, sorry I'm not there.
Well, good afternoon, everybody. I'm going to try to make up a little time, and I think I can do that because some of what I have in my materials will be somewhat summary, so I'm going to really just fly over that portion, and I'm going to dwell on the stuff that you haven't heard today. But first, I got to do a couple of things. One is I need to state a disclaimer. So I'm a very recent senior executive official in the executive branch, so I need to definitively state that I no longer speak for Department of Energy or the U.S. government in any way. That what I'm telling you today is my assessment based on publicly available information. Secondly, I'd really like to congratulate the people from PEC, and especially the individuals here who have pulled off this forum, including the presenters. I think this has been a phenomenal day already, so I'm going to try to pick up the pace and hopefully not drag that assessment down any here toward the end. And the other thing I just want to tee up is, David Grossman, I'm going to try to answer your question before you ask it. So we'll see if I manage to do that, okay? So to fly through quickly, punchline up front, you've heard, I think, almost everything in here. The one thing I want to dwell on this slide is industrial sources, in my opinion, present a near-term opportunity to take some CO2 out of the energy economy and develop business models and test technologies. Why do I say that? Many industrial sources emit CO2 in relatively pure streams, in some cases at pressure. So the cost of capture is lower than almost any other source you can think of other than the naturally occurring stuff. And it just provides an opportunity for us to accomplish the three things I just mentioned. The other thing on this slide that I would just point to is the last two bullets. There are transformational technologies in the pipeline. As John just mentioned, and I think others did today as well. We know the fundamental technologies work. What we haven't accomplished is having them work at reasonable cost in terms of the overall economic framework that is required. So there are transformational technologies in the pipeline. I'm going to show you a couple that I think are very promising. And lastly, CUS deployment at scale, in my opinion, will very much depend on business model and policy development that provides a value side of the equation, so that when you're looking at it from a business perspective, as I did when I was at Duke, you're not just seeing it as pure unrecoverable cost. This is a global atlas of CO2 emissions. The good news is in the developing world, where emissions have actually gone down in the last couple of years. The overall message, though, is the developing world makes up for the difference. So this is a global issue, and we have to think of it, I believe, in a global context. Just another slide that makes the same point, and then also, you know, I love one of Armin Cohen's slides that I've seen before, where he's got these guys holding up, you know, 2 degrees, and then somebody else pipes up and goes, well, how about 1.5? And it's like, okay, interesting, but let's talk about the pathways to do that. One of the things that becomes very clear, if you really intend on 1.5, is CCUS is absolutely required. In fact, you've got to capture on all sources in some way to get to 1.5. Global issue, I raised this slide for a couple of reasons. One is there's a lot of dismay in Washington and among the folks I speak to frequently about the change of administration and the belief that, oh dear, at best things are going to slow down, at worst things are going to come off the rails. My view is different than that. I do agree that things are likely to slow down, but there are a lot of folks around the world that are making real investments in this stuff, both in terms of technical expertise and money and real projects. So I don't think it ends here, while I do think it might slow down. I would especially point to the right-hand column on this slide, where the countries on the left-hand side are actually investing in and operating real large-scale projects. You've all seen this. This just makes the point again that we're going to need CCS as part of the mix. I'm not even going to dwell on this slide at all. You've heard this already. I'll leave this up for a minute just so you can tick down these projects. But these projects are all operational today. The one caveat is that Kemper is not. Kemper has operated on lignite, and it has demonstrated an ability to capture, but the plan is not for it to continue to do that. So, as John mentioned, it's a bit of a. I don't think of it as so much a complete failure as I do a learning opportunity, but that's just my bet as a technology developer, and we've learned a lot. This is one of the potentially transformational technologies that I want to share with you. This is actually being developed at Lawrence Livermore National Lab. It's very interesting. Somebody earlier spoke to the energy penalty from capture. This technology has the potential to really radically reduce that energy penalty and also significantly reduce the cost of the capture technology itself. And it does that by micro-encapsulating a solvent in a way with a kind of porous material that enables the transfer of CO2 at much lower temperature differentials. So very interesting there. This is another one that the guys at Livermore are working on. It's a 3D printed composite, so you can impregnate these materials with different carbon capture materials and mass manufacture them. Also, because of the configuration, the kind of waffle-like configuration, with the potential for much lower energy penalty and much easier regeneration at lower differential temperatures. Okay, this is one of my David Grossman slides. So David, just for you, I'm going to go back for a minute to, I'm going the wrong way. I'm going to go back for a minute to this slide, which one of your questions so far today has been, well, what's the political environment and how do we know that people are going to keep investing in this stuff? Here's one way. A bunch of other countries are going to keep doing it. Another way is over the course of the last 2 years while I was at DOE, I spent a ton of time up on the Hill talking to, congressional staff and congressional delegation members who are very committed to this kind of technology development, and I worked with them at length on how these programs can continue to be funded and advanced. So, having said that, then what are kind of the political arguments? Well, from the left, here's some of what I've heard in my conversations in Washington, with especially with congressional staff. We can just do this all with renewables and energy efficiency, just leave the fossil energy in the ground. You've heard a bunch of rebuttal of that already today, but I just list in the sub-bullets some of the other things that would be contrary to that. So if you look at IEA, IPCC, the White House Mid-Century Decarbonization Strategy, those all argue that no, in fact, we do need to continue to use fossil energy for a number of reasons, especially globally, and that CCS will be required. And of course, high variable renewable energy requires backup. That backup has to have a number of characteristics to adequately support the grid. So just another reason you can tick down through the rest yourself, with the exception of one that I would just kind of accent, which is ultimately, especially for a 1.5 degree scenario, toward mid-century, this century, you actually have to have negative CO2 emissions. It's hard to imagine how to do that without air capture and BECCS. And so CCUS is really required for that as well. Another argument from the left is, well, CCUS is a coal technology. It just enables coal. And I got really sick of that argument while I was at DOE, because CCUS is a decarbonization technology. It's not just for coal, it's not just for natural gas, although it works for both of those. It works on industrial, it works on bioenergy, it works on, it works on the air, we know. So it is a decarbonization technology. And the fact of the matter is natural gas use for power generation is increasing. So even though natural gas only emits about half the CO2 per unit energy produced as coal, it's gaining share, and it's gaining share globally. And if we really want to address the issue, CCUS has got to be part of the solution. Another argument from the left is CO2 won't stay in the ground. Well, there are a number of studies that show that it will, not the least of which is Tomakomai in Japan, where they've been capturing for, I think, not quite a year now, and they're already seeing mineralization in that formation. It's being injected offshore. We had thought, I thought when I first started studying this stuff, that it would be at least decades, if not centuries, for mineralization to occur. In many formations, especially basalt formations, it's occurring much more quickly. And then there's the, I forget what SAC rock stands for, but it is essentially an injection for enhanced oil recovery that's been going on since the 1950s, and the CO2 is staying in the ground. So that's the counter argument there. Life cycle emissions will be higher. Granger and I can talk more about this after we have a drink, but there are some analyses that indicate that to the contrary. So the arguments from the right: global warming is a Chinese plot, and CO2 is not the cause. Well, one of my counters to that is China's making huge investments in renewable energy and CCUS, and they're not doing it because it's to their economic advantage, necessarily. Although I would tell you that both China and Japan see the development of CCUS technologies as business development. They want their domestic manufacturing entities to be able to market that stuff globally. So they see it as a matter of actually manufacturing competitive advantage, and that's part of their thought process. Another argument from the right is, let's just build it without CCS. That's how we used to do it. Well, the risks are too great, is the bottom line there. So utilities won't do that. PUCs wouldn't approve it if they did, and markets won't finance it. Too much risk. Another one I've heard is, let's just grandfather forever. Well, okay, interesting thought. But, we govern in 4-year increments in the U.S., and in some cases 2-year increments. Future governments can make different decisions, and ultimately I believe global markets will determine how this comes out. What technologies actually get applied and how you actually manage CO2. And then another one that I've heard big time, especially out in coal country when I've gone there, is huge imperative to bring, let me add a word in here, huge imperative to bring coal jobs back to coal country. And I was quoted the day after the election in the New York Times and the Washington Post as saying, Trump's made a lot of promises. It's really difficult to understand how he's going to repeal the price of natural gas. Because right now, that's what's driving it. And so, so I think the coal folks and the current administration needs to think in different terms. And one of those different terms is, what about CCUS? What about especially the U in CCUS? Can we make chemicals out of it? Can we out of CO2? Can we make polycarbonate materials? Can we, what are the pathways to revitalization of industries in depressed areas that could be achieved where there is CO2 and carbon available, even new materials made directly from carbon? And then another really interesting one there is we have done a bunch of assay work through DOE and found significant concentrations of rare earth elements in coal-related materials, so overburden, ash, other coal-related materials, and in quantities that are truly financially significant. So what about an industry that would do remediation of coal mines and get out the rare earths and sell them? So that's my preemptive answer to your question, David. And last but not least, I am firmly convinced that the best way to do this ultimately is going to be through an integrated systems approach. And I had a number of conversations with the guys at NREL and with ERE. In fact, I sent one of my AAAS fellows out to NREL to work specifically on this. I don't understand why we can't merge those technologies and why they can't work synergistically so that you've got kind of the best mix of all the options. And in some cases, that best mix will be by putting things on the grid, the existing grid. In other cases, it will be by co-locating them so you can do things like share what would otherwise be rejected heat. So very busy graph. So part of what we did here is broke it out so that we can kind of talk to, the energy resources go into a power plant of some sort, and power goes to the grid. But oh, by the way, a power plant today, increasingly, especially in China, is not just making electricity. It's actually a poly generation facility. And so why don't we use renewables and other forms of energy for the gas separation part of the plant, for example? And why don't we think about how we can take the tail end of whatever we've got and either utilize it, use it to produce additional oil via enhanced oil recovery, or store it long term. And so this is just a kind of really busy way of saying I really, really, really think we need to really examine that larger integrated picture more than we have so far. Thank you very much. I hope I gained a little time at least, and thanks.
Thank you. It's great to be here. And I guess I want to thank the organizers again and congratulate them on this conference. I really appreciate the diversity of speakers and the different perspectives that have been invited and welcomed. And my perspective is very different. I agree with the basic premise of no silver bullet, but I have a much different perspective in terms of the decarbonization is much more about than climate change. And it's about the social costs of carbon. And that has to do with fossil fuel reliance much more deeply. And because of that, I do not think that investing more in carbon capture and storage is wise. So I guess I also wanted to mention, I used controversy here, and I want to just highlight at the beginning, I think there's some very different perspectives on many of these technologies, maybe particularly CCS and nuclear. And the reason there are different perspectives is not because some of us are right and some of us are wrong. It's because we're paying attention to different things. And there are different assumptions about how much in the world can change, or what we take as, oh, it's not possible to change, therefore we need to do this. Another reason that I think our perspectives are very different actually has to do with social dimensions of our society. I am very concerned about growing inequality in our society, and I think the renewable energy transition is a way to ameliorate that. So anything that we're doing to perpetuate and continue with fossil fuels, I think, detracts from that effort. So my focus, and at Northeastern University, I'm the associate director of a new Global Resilience Institute. My focus is really on the social resilience associated with our energy systems. And I think there's huge potential that isn't necessarily being talked about here yet, and I value the opportunity to add this, for thinking about individuals and communities and the distributed benefits of a system that is not controlled by a very few multinational energy companies, and that's where, when we move away from fossil fuels toward a more renewable-based system, that's where we have opportunities to go, and much more jobs and much more distributed engagement for all of us in terms of our society. So I guess I also wanted to just say I do have a science and engineering background, and the reason I'm on this panel is because my PhD work was on the risks of carbon capture and storage, and then for over a decade I worked on carbon capture and storage. But more recently, over the last 5 years or so, I have moved away from working on carbon capture and storage because I don't see it as a promising future, and I've focused more on thinking about the renewable energy transition. And one other part of decarbonization that I want to mention is that for me and for many colleagues that we are in a very carbon-based culture. So when we talk about decarbonization, we actually have to talk about culture and our society and our institutions. And it's not just about technology. And it's very easy because technology and economics are what we can model and measure, but those aren't the only factors here. So I welcome the opportunity to add that in too. I guess on one, I'm sorry, I haven't gotten to my slides yet. I did want to put one other thing right up front, and I feel a responsibility to do that given the political environment we're in right now. And that is that I fundamentally mistrust the fossil fuel industry. And I know Pennsylvania is a fossil fuel-oriented state, and there's a lot of connections economically and everything. But the recent developments, I'll just mention really quickly, what we've learned about the fossil fuel industry's strategic effort to confuse us on climate science, and that's why we are where we are with climate-denying leaders, I think is very explicitly connected to the industry strategy. We now have representatives of the fossil fuel industry at the highest levels of government, and I don't trust many of the things that are said and done. So I have that there. And even more recently, there was just an article in The Guardian about the level of fossil fuel funding of climate and energy research at all of our universities, and questioning how that has influenced all of us in terms of our discussions, even in a setting like this, in terms of saying, we need to perpetuate or continue because we look at all the fossil fuels, there's no way we're going to keep them in the ground. So I don't necessarily buy some of those fundamental arguments. So my own work is really focused on thinking about energy system transitions in a broad way, and really that involves technological change as well as social change. And when we think about this transition, and if you take the premise that we are shifting away from a fossil fuel-dominated system to a more renewable-based dominated system, CCS comes in as a potential bridge technology. And then we have to ask ourselves in terms of, is it prudent to invest a lot of money and time and effort and energy for this potential bridge that could slow down the transition? Another thing to think about, and I always tell my students when we're talking about energy system change, is that a transition like this is not simple. We can expect it to be very disruptive and kind of go in different directions, and we might have times where it looks like we're not going toward a renewable energy transition. That doesn't mean we're not, ultimately, right? It's a nonlinear system, and the other thing that's really important to think about with the renewable energy transition is moving away from fossil fuels, is that the renewables, once we have the technology, are abundant and plentiful and kind of perpetual energy. So it's a fundamental economic system when we move to that, and I think that needs to be acknowledged too. The other final point, and then I'll get right more into CCS, is the assumptions about consumption, energy consumption. That is beyond just energy efficiency, the way it was talked about earlier in the session about policy, incremental changes. It's very possible that we are getting to a point where we're going to have to think about more fundamental, radical shifts in our consumption. And that often isn't talked about in these technologically oriented sessions. So with regard to carbon capture and storage, as I mentioned, it's obviously a controversial set of technologies. As we've heard here, it's viewed as absolutely essential to climate stabilization by many climate and energy experts. But by many others in the world, it is viewed as an end-of-pipe, fossil fuel industry supporting technology that detracts from renewables and slows the transition. The US is among the countries investing most heavily in CCS because of our high coal and oil industry influence and natural gas. And CCS, one thing that's really interesting to acknowledge is that how it has fundamentally changed our climate and energy politics. Offering a coal climate future vision, it enabled a lot of climate deniers and coal invested stakeholders to come to the table and talk about climate change. So it's had a very powerful role. The CCS community, the people who work on CCS, like any technology, tend to become advocates of the technology. And we've done some research to actually characterize the community and assess kind of the degree to which the community thinks about the concerns that people who are not in the CCS community have. And as was kind of mentioned, despite the large investments, CCS has not advanced to the level that it kind of could or should, or people thought it might 10 or 15 years ago. So there's a real question, are we now kind of politically locked into continuing to fund this research and advancement, even if we may never actually get there? As we heard, there's a long way to go. So I also just wanted to mention there's controversy about carbon capture and storage among the public on multiple levels. The first is kind of local opposition to specific demonstration projects, and this is NIMBY, not under my backyard, right? We all know about NIMBY. But there's been very discrete opposition and protests and communities saying, no, we don't want carbon dioxide under our community. And then there's the more general opposition that it thinks about it as promoting fossil fuels and an additional subsidy to the fossil fuel industry and potentially detracting from the renewable energy transition. There's also questions of legitimacy, and the coal industry has promoted this notion of clean coal, which a lot of people really haven't bought, kind of, and I think that in some sense that campaign has backfired in terms of delegitimizing, because everybody knows there are all kinds of negative social costs associated with coal beyond just the carbon emissions. And this is also where a lot of environmental justice issues come in that, again, don't generally tend to get integrated into discussions like this about technological options. But different technologies and fossil fuel and coal and natural gas, the fossil fuel extraction process has a lot of implications for communities, and it generally impacts, the negative impacts are for the more vulnerable people in our society. So there are some very distinct environmental justice issues associated with perpetuating fossil fuels and the renewables have a whole different possibility and potential to ameliorate. So one of the things a group of us did who were involved in the CCS community and was to kind of explore who is participating in CCS research internationally. So this is just showing business, government, and academia. And you can see it's a good distribution of people who are attending. This is the International Greenhouse Gas Control Technology Conference. This is the countries who are involved. Sorry, it's small type, but USA, Germany, Norway, Australia, Netherlands, and the UK are kind of among the top supporters. And what this paper that we wrote on the CCS community, we asked about to what degree is the community thinking about some of the issues that opponents are concerned about? And as I mentioned, again, like many technologies, any of us who work on a particular technology often become very strong advocates of that technology. So the CCS community can be characterized in that way as an epistemic community that kind of shares a knowledge a network of knowledge-based network and recognized experts who hold this kind of common set of principles and beliefs. So other things to consider with CCS, as was already mentioned, the energy penalty, which is really quite hard to imagine the degree to which when it would make sense to build a whole additional coal-fired power plant for every 3 that had CCS. That's how big the energy penalty is. So like, it's conceptually a difficult thing to think about. There are also obviously health and safety concerns with perpetuating and continuing the fossil fuel extraction, as I mentioned. And this is an article that I wrote a couple of years ago, and I realized that this is exact opposite view that many people in this room share. Where I actually wrote an article saying that we should consider stopping investing in carbon capture and storage and reinvest that money in other directions, because I highlighted that how it can encourage complacency and a kind of this false sense of optimism that, oh, we're moving towards something, but we might not actually be. And it kind of assumes this inevitability of sustained fossil fuel use. And the notion of us solving the climate change problem is also, it had problematic in that we're so far along and we're so locked in that climate change is a reality and we're never going to solve it. We can reduce, obviously, but we need to start thinking about climate change in different ways. So when I wrote this article, I had some of my climate energy experts tell me I was absurd and ridiculous. So I'm sure some of you may look at this and think the same thing, and I'm prepared. So I understand the other side of the arguments. But I also think it's important to ask this question and to really be thinking about how we want to invest the limited money that we have to improve societal resilience moving forward in the future. So I will end here, and I just want to say, to conclude, that the energy sector is very dynamic, and flexibility and adaptability are increasingly valuable, and I don't see carbon capture and storage offering much in terms of flexibility and adaptability. Transitioning away from fossil fuel reliance, I think, should be prioritized for many reasons beyond climate change and beyond the decarbonization. And we should expect this to be disruptive. There's no way this is not going to be disruptive. And we're already starting to see some of the disruptions. We also start to see digging in the heels even more of the people who are currently profiting with our fossil fuel system. So, it's not going to be easy, but I think it's essential. And I think if we don't do it, the United States, is going to be behind other countries who are going to more successfully and effectively move forward without fossil fuels. So with that, I would also just encourage all of you in all of your work to try to connect your thinking on energy investments with social justice. It's something that increasingly in my own work I've started to realize that if we act without considering the injustice and inequalities of the systems that we are living in, we are inadvertently perpetuating those inequalities and injustices. So this is like a call to really encourage everybody in everything that we do to pay attention and realize and consider outside the box of your technological or economic framing that we tend to dominate many of our policy discourses when we think about energy, to broaden that and really think about how we can use energy system change to really help society at a deeper level than carbon. So, thank you, and my website and email are here, and I've had funding on my CCS work from the National Science Foundation and also from MISTRA, which is the Swedish Foundation for Strategic Environmental Research, which is one of the few funding agencies on CCS that was clearly not an advocate. They wanted non-advocacy work on CCS. So we did very interesting projects with them. Thank you very much.
So thank you to the entire panel, but I'm pretty excited that we're going into the hors d'oeuvres and cocktail hour with such juicy fodder for conversation.
So what do you think, half a question, since I proactively answered one?
They're so, I think this might turn into many, many questions, but why don't we just go ahead and do a few?
So a question either to John or David. When people first started talking about deep geologic sequestration, the argument that you got was, well, you just push it in there under high pressure and the earth will move up a little bit and that'll be fine. We've learned, of course, that in fact you probably need to extract brine, which means then that one needs to desalinate the brine because it's really obnoxious stuff. To what extent is anybody in the CCS community working seriously on the additional energy penalties associated with the brine desalinating and the costs that are associated with that in terms of, you know, life cycle costing of the technology?
Shall I start and then? Okay. During my last year at DOE, so basically 2016. We began some work with KUMTC, King Thod University of Minerals and Technology, looking at exactly what you're talking about. And we actually also have a project that we're monitoring with China to do CCS with essentially reverse osmosis for removing brine and getting usable water, not potable water. It really looks like it's got even larger cost hurdles than some other aspects of that particular suite of technology development. The only place it makes any real sense today is where there are huge water deficits. But early stage stuff.
But I may have to do it in any event because they may not.
There are actually other ways to manage the formations, and I'm not the expert on that, but Julio and Roger Ains at Livermore can spend a day with you and tell you all about it.
We can do it in Oklahoma.
Yeah. I don't know if John wants to. Okay.
Carbon capture, use, and storage is a good word, but I'm worried about the use. As I understand it, the total industrial demand for CO2 is on the order of 100 megatons a year, which is a pretty tiny fraction of the 50 gigatons a year of CO2 that the world economy produces. So if we start doing CCUS very seriously, we will soon completely flood the market for CO2, and the value of CO2 will go to zero. That seems pretty solidly true. And then since carbon capture requires a certain extra capital investment and it has a certain energy cost and whatnot, it's going to be expensive. And how can it possibly survive without price supports? Not that we shouldn't have a cost of carbon, right? We ought to be paying for CO2 we release into the atmosphere, but how can CCS possibly survive without that?
Well, as I mentioned, I believe that we do need both business model and policy development to make it work. There is still enormous potential for enhanced oil recovery in the U.S. and elsewhere, including
But that's
residual
probably
oil
not
zones.
50 gigatons a year either.
What goes into the Permian? Does anybody here really have the number? The non-anthropogenic CO2 that goes into the Permian is something like 60 million tons a year and has been for year over year since like
Right,
the
but that's
70s.
0.1% of the, yeah, okay.
Well,
I mean,
and that's I'm picking on one example
Okay.
of a huge sink, and John Quigley also talked about just the geological potential. So there are lots of issues. It's not an easy putt, but I do believe that there is a possibility of putting together a portfolio of policies and business models that begin to reduce the disparity we've got today, which is essentially when most business people, like I was at Duke, look at the equation, it's 100% cost and zero value. I think we can at least begin to shift that, and then policy's got to make up the difference.
Without regard to reuse, I know that the Boundary Dams project, the amicus brief they filed in the Clean Power Plan litigation indicated that 10% of the carbon dioxide is being injected without use for EOR. 90% is being used for EOR. And if President Trump moves forward to try to repeal the Clean Power Plan, one of the issues will be what is the cost per ton for removal? I mean, both Saskatchewan Power and NRG say that they'll build the next plant at 20% lower CapEx than the current. But I haven't seen any, what is the dollar per ton cost if you simply inject it into one of the deep sandstone with a 20% CapEx reduction?
Well, I don't know if I could do the math in my head quick enough, but today the cost for capture and injection is something north of $70 for coal and something higher than that for natural gas. I don't know if anybody in the room has better numbers in their head than I do. So I mean, that's a short answer. So you'd have to take the 20% reduction in capital costs, figure out how that played through into that operating cost, and do that math. What I do know from talking directly to the Boundary Dam, the Sask Power people and the people from NRG, is neither plans to do another project like Boundary Dam or Petronova until oil is above $50 a barrel. So that's another way to kind of get to their imputed cost.
So it may be roughly $50 a ton, which...
No, you can't go there.
Oh, but it would be $50 a barrel, that's right.
$50 a barrel, yeah. So what does it take? 2 tons of CO2 to produce a barrel of oil in most formations? Something like that? Granger, you're going to bail me out on the math? No.
So
I guess the point is you may be.
So I think when we
getting...
start to get into the point of doing math at the end of the day, that maybe we all need a drink. I want to just take the moderator's prerogative to make an observation about this panel relative to the other technologies we talked about today, because we are thinking about deep decarbonization in Pennsylvania, and we have an historic role for coal and now natural gas in this state. I think this is something that we can see as a potentially unique responsibility and opportunity for us to think about this technology, particularly in Pennsylvania and this region. And then teeing off Jennie's comments, maybe that means if Pennsylvania decides to become a pioneer in this space, it might also mean that Pennsylvania citizens are assuming a unique risk at the expense of everybody else in the country who might benefit from our advancing this technology. So with that, we'll take the math into the cocktail hour, and thank everybody for coming today.